if a function is continuous and you want to find a limit, you can just plug in. Not only that, we've got a nice list of functions that are continuous that are going to really make your life a lot easier. So you're welcome. Here's this fun theorem. The following types of functions are continuous on their domains. Are you ready for this list? Polynomials, rational functions, roots, trigonometric functions, inverse trig, exponential, and logarithmic functions. In other words, every kind of common function you've ever studied are continuous on their domains. So that tells you a little bit about why continuity is important, because most nice functions are continuous on their domains. Not only that, I added in this extra note, also the sum, difference, product, quotient, and compositions of continuous functions are also continuous, which means you can just plug in to find their limit. That is so nice. Okay, so that is wonderful. That's pretty much every function you've ever heard of. What we have to be a little careful here. There are a couple things that this doesn't cover. One is, what if we are not in their domain, in which case they're definitely not continuous there. They might still have a limit though. The second is that we've seen the most of would be piecewise defined functions. Okay, there are a couple other functions I could probably throw in here that are or aren't continuous. So step functions are not continuous at each of their steps. There's a couple other weird ones maybe you've seen. But let's take a look at this wonderful gift of a theorem. Really couldn't ask for anything more. So, examples. The limit as x goes to 1 of tan inverse of x minus 1 over x plus 2. Okay, so we just need to know what is the domain. This is a composition of functions. I need to know what is the domain of this. This is an inverse trig and this is a rational. So what is the domain? Maybe it's been a while since you've thought of a trigonometric inverse. I'm going to tell you right now, there is a best one. There's one that is my favorite. It shows up the most places. It's the winner. It's a really nice function. Tangent inverse is a great function, and you should know roughly what it looks like. So I'm going to sketch on the side real quick here. It looks a little bit like this. Something like that, where you should know where it crosses the x-axis and the y-axis, as well as those horizontal asymptotes. So it crosses right through the origin because tangent of 0 is 0. Tangent is telling you what the slope is there. And it has these beautiful horizontal asymptotes. And those are at pi over 2. Oops. And negative pi over 2. Okay, so really nice function that is bounded above and below and continuous everywhere, and has a lot of other nice properties. So we like that one a lot. Much nicer than tangent, that is discontinuous all over the place, has all those asymptotes. Okay, so this is defined everywhere. It's continuous everywhere. The question is, this inner function, where is that function's domain? And so this is rational, and it will be nice everywhere except for where the denominator is 0. I hope you're catching on to this routine. So this is going to be continuous everywhere except for when x is negative 2. Okay. Oh, shoot. Sorry, it's continuous there. Got to actually answer the problem. So it's continuous at x not equal to negative 2. What does that mean? It means I can just plug in. It is definitely continuous at 1. So this limit is going to be equal to tan inverse of 1 minus 1 over over 1 plus 2. Continuity lets me just plug in. You could put this in your calculator. I hope you don't have to. Tan inverse of 0. What is tangent inverse of 0? We love our calculators, we do, but you got to know this one. Tangent of 0 is 0. Tan inverse of 0 is also 0. Great. piece of cake. This would be so nasty to do any other kind of analysis with, but it's so easy because we know this property of the functions that build it up, right? This outer function in my composition is continuous. This inner function is continuous except for at -2. We're not anywhere near -2. Just plug in. Okay, where is the natural log of x continuous? Well, this theorem tells me on its domain. Now, do you know the domain of natural log of x? Of course you do. We love natural log of x. And the domain of natural log of x is going to be x greater than 0. Okay. If I was going to graph this real quick, so looks a little bit like this, a little bit like this, and goes, oops, I don't want that. I'm just going to change back. Okay, so it's got a vertical asymptote here. It goes through 1, 0, and then it grows forever, but slower and slower and slower. Okay, that is my natural log of x. And it's continuous everywhere on its domain, which is x greater than 0. As a side note, I think this side note is always worth reminding you, it is the inverse of e to the x. E to the x looks kind of like that. What does an inverse do? It switches your x's and your y's. And so switching your x's and your y's is the same as reflecting over the line y equals x. So if it helps you remember it, just remember that reflection, and that should help you figure out that the range of e to the x is 0 to infinity. So the domain of natural log of x is 0 to infinity. Great. Wonderful. Okay. So that's a nice gift. Feel free to use it from now on. Much better than trying to use a table. And we have one more thing for you, and then I'll talk a little bit more about why this is all important. Okay, we have done most of this section. Probably what you need to do is just practice a bunch, both identifying and working with limits and doing that algebra to simplify them. But I really like this theorem. It also has a name. It's called the intermediate value theorem. If it has a name, it must be important. A lot of times it is so important people will know it if you just write IVT. That's how important it is. A lot of times when people are talking about continuity, what they really care about is that it obeys the intermediate value theorem. And so when people were trying to think about what are the properties of functions that make it look like a normal thing in life or give it nice mathematical properties, this is a big one. So let's walk through this. If f is continuous from a to b, which means I've got a in the domain and b in the domain, and it is continuous for all the points from a to b. I haven't drawn it yet. So there's going to be some point at a and some point at b. And the y values of those, well, the function tells me what those are. So the y value for the first one is f of a, and the y value for the second one is f of b, whatever those are. Okay, so far so good. Okay, so I've got some continuous function, and it's moving from this point to this point, and pick any other point you want, any other y value you want n. Okay, so let's say this is n. And here is this y value, this line y equals n. And the only thing I'm saying is it has to be in between f of a and f of b. Okay, what this theorem says is that somewhere in between a and b, somewhere, call it c, f has to cross this line. F of c is equal to n. So somewhere in between here, I've got to cross that line. Well, let's just see if I can defeat that. Here's this dotted line. I'm going to keep it continuous, and so I'm going to try to get from this dot to that dot without crossing it. Here I go. I'm going to try to go down there, and I go, oh, I can't cross that line, so I'm going to go back up. And I go, okay, I'd like to jump over that line, but I can't. I can't jump over it because I'm continuous. And if I had to jump, I wouldn't be continuous. So, okay, maybe I'll go back up here and I'll sneak up on it. No, oh, no, shoot. And I go back up, and I'm going to, and the only way I've got to get there is at some point, I just got to cross it. Maybe I cross it a bunch of times, but wherever I end up giving up on crossing it, that is my C. Okay, so this right here looks like that's C. Okay. So if you're continuous and you want to cross a horizontal line, you want to cross a y value, or you are crossing a y value, somewhere you have to actually touch it. You can't jump over it. And I hope that makes sense. So this value is the intermediate value. Intermediate means in between. Okay, so that's it. That's the intermediate value theorem. I need you to basically roughly know what that says. I don't need you to memorize this wordage here, though you should practice reading it. In fact, here's a little treat for those of you who care. It's worth learning a little bit of notation. So for those of you who like notation, let's rewrite these last two lines with some math notation just to show you. I could rewrite this really quick. Like this. This capital backwards E says there exists C, and I want it in AB. So this is that interval notation, and in is this fun thing. In fact, I probably should write that a little lower. Okay, so this right here is in, such that we often write as such that f of C equals n. Okay, I show you this one because it's fun. I like it a lot. 2, because it might help with your notes, keeping them a little cleaner. 3, if you take more math, you'll start seeing more and more notation, especially as people just write notes to each other. So this there exists ends up being pretty important in logic. This in you see a lot, and then such that is a pretty common abbreviation. So there's those last 2 lines written super fast. Okay, that was a tangent. I hope you enjoyed it. Second, I'll give you 2 reasons why this theorem is important. 1, it's sort of telling you or something that is commonsensical. In real life, many of the things we care about obey this rule. Okay, in real life, if you remember the example from the very beginning of class, if I'm walking along a line, I can't get from the beginning to the end without hitting every single point in the middle. And so what that's telling you is that continuous functions are the ones that like have to obey this, and most things in real life are continuous. Not all of them, but anytime you're worried about the position of a particle or the height of a child, right? These are continuous, and you know that if they got from one point to another, they must have hit everything in between. This is that thing in your head that says, "Oh yeah, this makes sense." That a lot of functions that matter in the world obey this. And that is one of the reasons why we really like continuity. It ends up being necessary for many other big important theorems. You say, okay, if a function is continuous, then I get lots of nice stuff out. If it's not continuous, then there's a lot of really weird bad things that can happen. And I will show you some examples later of just how weird things can get. I really like those bad examples. They're fun too. Okay, let me give you one more reason why this is important that will definitely not be on a test, but for your mathematical education. Here is an example. Let's just show that this function, x to the 5th minus x plus 1, has a root. Looks simple enough. What does it mean to have a root? This just means that somewhere it equals 0. Right? A root is just a place where that function equals 0. Okay. Well, you might try to solve this, set it equal to 0 and solve. I encourage you to try. I'm quite confident if you do try, you're going to fail. There is a reason for this. This function does have a root. It actually has 5. And they cannot be written in any combination of addition, subtraction, multiplication, division, square roots, powers, or any of those. So what that's telling you is that there isn't really a nice way of writing it. Just like there isn't really a nice way of writing pi. If there was, we wouldn't write pi, we'd write whatever that nice thing was. So I can't give you a formula for this. There is no degree 5 polynomial formula. It simply does not exist. Okay. However, we know this thing has a root. In fact, if you were to graph it, you would see that it should cross the y-axis, but graphing isn't really a proof. So let's prove this real quick. And it's surprisingly simple. let's just plug in. F of 0 is, I plug in 0, 0, 1. Let's plug in -2. That sounds much better. So if I plug in -2, it looks like I get -32 plus 2 plus 1 is equal to -29. So by the intermediate value theorem, f of x has a root. It has to be 0 somewhere in between these two, and it has to have a root in this interval. Somewhere in between -2 and 0, it went from a negative number to a positive number. So somewhere in between those two, it must have crossed 0. Fast and easy. And maybe you did this intuitively. This polynomial is part of something called the Abel-Ruffini proof, that there is no degree 5 formula for roots. You know the degree 2 one. It's called the Quadratic Formula. There is a degree 3 one. It's quite big. There's a degree 4 one, which is just freaking terrible. It's more like a flow chart to get through to your degree 4 solutions. But when you get to degree 5, there isn't one. And we know this because we can actually prove that there are roots, that there is no good way of writing them down using the basic operations that would make up a formula. So I think that's super neat. It's also just a nice example of how the intermediate value theorem is often used to prove simple facts that would be otherwise really, really hard to prove. Okay, that's it for now. Go and practice a lot. Usually these just take a lot of practice to feel good with. Go talk with other people because the language is also a bit tricky.